Thank you for the introduction. And today I'll be talking about a brand new way to apply hazard pointers that was actually slightly mentioned before to optimistic data structures using immutability. Now, even though we have just seen a great talk on memory management in non-blocking concurrency, I'll still provide some more background, albeit with a slightly longer example. In particular, let us consider a linked list with 4 nodes. And suppose a thread T1 that was currently at node 1 obtains a reference to node 2 and wants to access it. However, the scheduler abruptly stops T1 and runs another thread T2 who wants to remove nodes 2 and 3. To do so, T1 will first detach the 2 nodes and freeze them. However, as we have seen literally 20 minutes ago, in concurrent programming, it is unsafe to immediately free detached nodes, as when T1 wakes up, it will access node 2, which leads to a use after free error. Thus, for safety, we must ensure that T1 has finished using node 2 before freeing it. There are several methods for this kind of work, for this kind of reclamation in non-blocking concurrency. A classic example, the one we have seen in the previous talk, is RCU. RCU supports majority of data structures, in particular those that benefit from the efficient optimistic traversal strategy that I will come back to later. However, RCU is not robust, meaning that its memory usage is unbounded. Another example is hazard pointers, or HP for short. Unlike RCU, HP is robust but was incompatible with optimistic traversal. In this work, me and my colleagues have developed a brand new methodology that enables to efficiently apply hazard pointers to optimistic traversal. And before getting into our main idea, I'll first explain hazard pointers in detail. Going back to the first example, let's see how hazard pointers prevents use after free. On the one hand, before T1 accesses node 2, it first protects node 2 to ensure it is not freed. On the other hand, after T2 detaches nodes 2 and 3, it does not immediately free them, but retires them, deferring freeing them until all protection is over. At this point, node 3 can be reclaimed, but node 2 cannot, as it is being protected by thread 1. Once thread 1 finishes accessing node 2, node 2 protection will be released, and it can be freed as well. However, protection alone is not enough to guarantee safe access. To see this, consider the case where T1 wishes to further progress to node 3. Similar to before, it will protect node 3 and access it. But as node 3 is already freed, this is a trivial use after free error. Thus, after protecting node 3, T1 should validate that node 3 is not yet free to guarantee safe access. In practice, this is done typically by checking that a node is not detached. This works because a node must be retired to be freed and must be detached to be retired. To efficiently check if a node is detached, we typically utilize a marking mechanism. For example, before detaching nodes 2 and 3, we mark them as to be detached, sending a warning to traversing threads. Marking is typically implemented by tagging the least significant bit of the next pointer field. After marking, a separate step will detach the 2 nodes. Now let's see how hazard pointers' standard validation strategy, which I dubbed valmark, utilize marking for protection. Again, suppose T1 wants to step from node 2 to node 3. First, T1 will protect node 3. Then, it tries to validate the protection by checking that node 3 is not detached. To do so, it checks the mark of the previous node, node 2. Here, as node 2 is unmarked, T1 knows that node 2 is not detached, and node 3, which is pointed by node 2, is not detached as well. So, T1 has successfully validated the protection of node 3 and can safely access it. Let us also see the opposite side, where a marked node causes a validation to fail. Again, we are checking that node 3 is not detached by checking the mark of the previous node, node 2. Here, as node 2 is marked, T1 knows that node 2 is to be detached, and in this case it actually is, and node 3 is to be detached as well. So T1 simply gives up on trying to protect node 3 and restarts from the beginning. While hazard pointers and a standard validation strategy, val-mark, is widely used, a major problem of val-mark is its inapplicability to optimistic traversal strategy. Optimistic traversals are traversals that ignores marking for performance. For example, an optimistic traversal through the following list will step through nodes 2 and 3, like so, even though the two nodes are marked and reach 4. Now, it is not hard to see that optimistic traversals are much more performant than traversals that restart when they see a less marked node because they simply have less restarts. Now we get to our problem, which is that a crucial downside of val-mark is that it is too pessimistic to be applicable to optimistic traversal. To see why, consider what happens when you apply hazard pointers with val-mark to the previous traversal, in particular when we are about to step from node 3 to node 4 on the current configuration. First, like before, T1 will protect node 4 and proceed to validate that node 4 is not detached by checking the mark of the previous node, node 3. And here, as node 3 is marked, similar to before, T1 will think that node 3 is to be detached and node 4 is to be detached as well and restart from the beginning. However, in this case, node 3 is actually still attached, so validation could have actually succeeded. And not only is this a missed opportunity for validation, but it could also be a source of live lock, which is very unideal. To resolve this discrepancy, it is a very common practice to sacrifice optimistic traversal to use val-mark. That is, it is common to sacrifice the efficient optimistic traversal strategy for the robustness of hazard pointers. In this work, we have developed a new validation strategy that overcomes this limitation and can be efficiently applied to optimistic traversal. Our key idea is to leverage the inherent immutability of traversal-based data structures for validation. Now, let us look into this idea in more detail. By immutability of data structures, we mean that a marked node's next pointer fields becomes immutable. For example, say nodes 2 and 3 are just marked as to be detached. But before detachment, another thread, T1, tries to add node 2.5 before nodes 2 and 3. To do so, T1 will first create a new node and try to update the link that points from node 2 to node 3 to point to node 2.5. But as marked nodes are immutable, the link cannot be updated and the insertion will fail. Now, immutability is actually essential for the correctness of traversal-based data structures, and to see why, suppose marked nodes were actually mutable and the insertion of node 2.5 succeeded. In this case, when T2 finishes running and detaches nodes 2 and 3, we see that the node 2.5 that was just inserted actually becomes unreachable from the head node even though it has never been called to be detached. Immutability prevents such a problematic scenario from happening. Now, let us look at our new immutability-based validation strategy, val-immute, and see how it can validate node 4 in the previous example where val-mark has failed. As the same as before, we are traversing from node 3 to node 4 and want to validate our protection on node 4. In contrast to before, we don't check the previous node, node 3, but instead choose to check the first unmarked node, node 1. Here, T1 will see that as node 1 is not marked, thus it can conclude that node 1 is not detached and node 2, which is pointed by node 1, is not detached as well. And here comes our key observation. During T1's traversal to node 4, it should have seen that node 2 and node 3 were marked, hence immutable. In particular, this means that T1 can learn that even without directly checking the mark of node 2 and 3, node 2 will still point to node 3, and node 3 will still point to node 4 as they are immutable. And as it has learned that node 2 is not detached by checking the mark of node 1, it knows that node 4, which is transitively pointed by node 2, is not detached as well. Thus, T1 has successfully validated the protection of node 4 by checking the mark of node 1 and can safely access node 4, continuing its traversal without restarting. Now, let us see some experimental results. In these graphs, we compare hazard pointers with our optimistic validation strategy val_immut, colored in pink, and the pessimistic validation strategy val_marked, colored in orange. And thanks to optimistic traversal, data structures using val_immut outperform those using val_marked by a large margin, up to 24% for lists and 61% for trees. In conclusion, we see that val_immut is much more performant than val_marked thanks to the power of optimistic traversal. In the paper, we have a more detailed explanation of hazard pointers with val_immut, such as application to an optimistic binary tree and optimistic skip list, verification in the ROC theorem proving using the iris separation logic, and detailed comparison with other reclamation algorithms. So please check it out if you're interested. And although that was quite short, that's all, and I'll be happy to take your questions.
Yeah, any questions? Can you come to the mic? And say your name and affiliation.
So my name is Ruslan Nikolaev. I'm from Penn State. Great talk. It's actually a very interesting idea, right? So we actually had somewhat similar idea when we worked on the Trajan tree, but we can talk offline.
Yes, we should talk offline, yes.
Yes, so one question I have, I glanced through the paper. So it seems like you evaluated her Lithi-Shavit skip list,
yes.
Right? And I was wondering, did you try to evaluate Fraser's skip list? Because Fraser's skip list is kind of similar to, I guess, Harris list, linked list, right? So where you
yes, I think we did. We did a lot. And I think for the skip list, so the skip list, so there are a few variants. I'm assuming you're talking about the few different variants of skip list.
Yeah, so there is one skip list is kind of similar to Harris-Michael list, and the other one is kind of similar to Harris list.
I think we essentially implemented all variants, and there's even one if you want the ones that's similar with Harris-Hurley-Shavit list, we implemented all of them, I think.
Okay.
We can discuss more offline.
Okay.
If you want the details of the experiment. Yeah.
Okay, thank you so much.
Yes.
Yeah, so I must say we also wanted to do this. Great idea. Can you say to which data structures this cannot work with? Can you categorize them or just give an example?
So I guess the more broad is that can you prove that it is applicable in a general sense? So we thought of doing that, and we had a few ideas, but we decided that the term data structure is way too broad for our purpose. But we do believe that. So I guess the question is so we do use immutability. So I guess the question is how general is this assumption? And even though we don't have a formal proof, we do believe that most data structures, especially concurrents, are essentially bag-shaped. And if you want to update them using KAIST, you essentially have to utilize the marking and immutability mechanism, or else this counterexample happens. So I believe that if you want linear stability for your data structure, you kind of have to use this immutability property, and then hazard pointers will most likely work. But as I said, we haven't done a formal proof of it or something like that.
Okay, thank you. Let's thank the speaker again.